So to answer this question, we would first look at our the Henderson-Hasselbalch equation to get the ratio of the A minus to HA. So that would be, again, the pH equals pKa plus log of A minus over HA. So our pH is given, right? It's pH equals 4. Our pKa is given, 4.75. And then we're trying to get what this ratio is over here. So if you solve this down, you'll get a ratio of our HA times 0.18 equals A minus. So that's your first equation. So you get this equation, or you get this ratio, and then you just save it for the next step. So the next step is to use the Van Slyke equation, which remember is the theta equals 2.303 times C times Ka plus H3O. Aren't you glad you don't have to memorize this equation? So for this part, we're solving for C in this example. So remember the last equation, or the last example, we were trying to find the buffer capacity. So this one, we're trying to find the concentration of the weak acid and conjugate base. So we're solving for C. So we need our Ka, right, which is it's essentially the anti-log of the pKa, right? So it's 1 times 10 to the minus 4.75. So that's 1.8 times 10 to the minus 5. And then you also need your H3O, which is 1 times 10 to the minus pH, which is just 1 times 10 to the minus 4. So you plug these numbers all back into the Van Slyke, right? So we know our beta is 0.01, right? That's given in the question. We know our Ka, we know our H3O plus, and we're solving for C. So if you solve all of that down, you'll get C equals 0.033 molar. So this is our second equation. So then you combine these two equations. So remember, C equals HA plus A minus, right? So we have C equals 0.033 molar, and then we can substitute this in for A minus in this equation. So it's equal to HA plus HA 0.18. So 0.03 equals 1.18 HA, right? And then we get HA 0.028 molar. And then we just use this same equation and solve for A minus. So it's 0.033 molar minus HA 0.005 molar. So we know our molar amounts of our weak acid, right, and our conjugate base. And then we would multiply by the molecular weight to get our actual weights of both of them added. So the molecular weights are given up here. So acetic acid is HA, and sodium acetate is A minus. So if you do that, you should get this as your answer. Make sense? And then also remember from lecture, if we're formulating at our pH equal to the pKa of our weak acid, we use a more simplified equation than this one. So for this one, for this example, we're looking at a pH equals 4.75 as our formulation for our buffer, and that's equal to our pKa. So remember for that one, we're using the 0.573 times C, because we're using the Betamax equation. pH equals pKa, this is the equation then. So also remember at pH equals pKa, our weak acid, HA, is equal to our conjugate base. So we already know the ratio. We don't need to use Henderson Hasselbalch. We know the ratio. So this one's just a matter of plugging this into the equation. So 0.01 equals 0.573 times C. So you should get C equals 0.017 molar. And remember, this is equal to HA, which is also equal to A minus. So you just divide this by 2 to get the molar concentration of each. So when you see a question like this, though, it's even easier to do it for multiple choice because you know our pH is our pKa. So you could also just divide all these by the molecular weight and find an answer where you get a molar concentration where they're the same, right? So you can just take all of these, divide by the molecular weight, and when you see that the molar concentration of acetic acid equals sodium acetate, you know that that's when you have a molar ratio of HA equals A minus. So it's a way to do this one easy if you wanted to. You should use this equation, but you won't actually have to for this question. So the pH of buffer solutions, again, remember, is driven by the pKa of your weak acid, and then also the ratio of your weak acid conjugate base. So those equations we were using to calculate what that ratio is, get your pH, or if you're given the pH, you can then calculate what that ratio is. And then these are the different buffer solutions that are commonly used in pharmaceutical formulations. So these are the given pKa's, and then for your buffer solutions, remember that you're making your pH within plus or minus 1 unit of the pKa of the acid that you're using. So for example, if you're using an acetate buffer, you would be able to make your buffer solution anywhere in the range of 3.75 to 5.75. So plus or minus 1 pH unit of your pKa. And then to get the ratio is what gives you different pHs in that range. So pH equals pKa means your ratio is 1 to 1, and then when you change that ratio, that's when you can get a higher or lower pH of your formulation. And then the buffer capacity of the solution, remember, is determined by your concentration of the weak acid and conjugate base in the solution. So looking at the total concentration of the two, when you have a higher concentration, that means you have a stronger buffer capacity. And that just means it maintains a more narrow pH range. So higher number means more narrow pH range. And then the pH range for oral formulations is usually within this